Hello dear students, today we will be discussing about cathode ray oscilloscope. Now already we had seen the block diagram of cathode ray oscilloscope. So the block diagram consists of vertical section as well as a horizontal section. So we are applying the input signal that is to be displayed to the vertical amplifier, and the horizontal amplifier or horizontal section will be developing a time-based circuit, time-based signal which gives the reference for the vertical signal that is to be displayed. It also has voltage signals or voltage supplies, high voltage as well as low voltage supply to be provided to the circuits. High voltage supply is given to CRT for accelerating as well as focusing anodes, and low voltage supply can be given to other auxiliary circuits including the heater element. Then we have the focusing anodes, the accelerating anodes, and this will be focusing the electron beam that is generated by the cathode, and it will be with the help of horizontal as well as vertical deflection plates. It will be deflected and the bright spot will be created on the screen. And once the movement of the spot is very fast, you see you will feel that a continuous signal is being created on the screen. So that's how the entire CRO works. Now we'll be focusing on how the time-based generator works, how you are able to display a particular signal on the screen. Now time-based generator is a sawtooth waveform that is applied internally across the horizontal plates. Now this is normally calibrated in seconds per centimeter, that is the time required for the spot to sweep 1 centimeter horizontally across the screen. Now this can be considered something as a time base for the signal. That is, when you draw any waveform, you need a time base. So that time base is being formed with the help of this particular time base generator. So this helps to display the actual waveform on the screen, which is the actual waveform is being fed to the vertical deflection plates. So whatever the waveform that is given to the vertical deflection plates, that needs to be recreated faithfully on the screen. So that is being done with the help of this time-based circuit. Now, as I've already told, the time-based circuit is a sawtooth signal that is being internally generated. Now, and this is applied to the horizontal plates, and we assume that at the vertical deflection plates, so this is your voltage at the vertical deflection plate. So this is 0. We are not applying any signal to the vertical deflection plate. And under this condition, what happens? As we move from A to B, as the sawtooth wave is progressed from A to B, your spot is moving from A to B. It reaches this point, and from B to this peak value, you can consider this as C. And from B to C, the spot is moving from B to C. Horizontally, the voltage is increasing, so the voltage that is applied at this plate is increasing, so the beam is being attracted to this point. And once it reaches this point, what happens? Your sawtooth is traced back to the original point, or the sawtooth starts to repeat again. And once there is a repetition, what happens? What it does is that this dot will be flying back to the original point, and again it starts from A. Now A becomes this point becomes A. Okay, so this is A. Initially this was A, now A, this becomes the new A, and again this is repeated. So as the sawtooth is progressing, you will get a continuous movement of spot on the screen, and which can be seen as a straight line. If you have only a single sawtooth, you will see that a dot is being moving and it has ended up at this point. But since we have multiple sawtooth repetitively following, you will have a straight line being created in the horizontal direction. So this forms a time base for the signal that is to be fed at the vertical deflection plane. Now the spot moves from left to right in uniform speed, with the uniform speed. So this forms a linear time base for the signal that is applied to the vertical deflection plate. Here we have a sine wave applied to vertical deflection plate. I will just correct it. This is T by 4, this is T by 2, this is T by 4, this is T by 2, this is t by 4, and this is t by 2. So this is time t is equal to 0. Now again here we have same sawtooth applied to the horizontal deflection plate, and we are applying a sine wave to the vertical deflection plate. As sine wave is applied at this plate, you will have a deflection towards depending on the voltage that is available at the vertical plate. So as the sawtooth wave progresses from 0 to t by 2 or t by 4 or t by 2, your sine wave also progresses from 0 to t by 4 and then to t by 2. So as the voltage applied at the vertical plate varies, the waveform will be your spot will be moving from 0 up to t by 4 and then t by 2, which reaches here, and then again the sawtooth wave is progressing from t by 4 to t. So your voltage wave also is progressing from t by 4 to t. So here signal recreation also is being done from t by 4 to t. If you have only a single sawtooth wave, what you will get? You will feel that a dot is being progressing from 0 to t through t by 2. Since we have multiple sawtooth waves available and your voltage signal is being continuously fed to the vertical plates, you will have a continuous sine wave being created at the at this CRO screen. So this is how you create signals, and the conditions that needs to be satisfied is that both the horizontal as well as the vertical signal needs to start from the same instant. So this is being done with the help of trigger circuit. It is there in the block diagram. You have a trigger circuit in the block diagram. So trigger circuit along with the time based generator make sure that your signals are starting from the same instant, and the ratio of the frequencies which are applied to the vertical as well as horizontal plates has to be some rational or a fractional number. So here on the screen you have, on the entire screen you have a single signal is being displayed. You also have the option of displaying multiple wave cycles on the same screen. So that also can be done with the help of this particular sawtooth waveform, provided you have your frequencies are a fraction or a ratio, rational or a fractional number of this particular vertical signal as well as a sawtooth waveform. Now the amplitude can be measured, as we have already seen. Here the volts per division is set to 0.1 volts per division, and when we are measuring peak voltage, the total number of divisions between the two peaks are, here we have 1, 2, 3, 4, and then here 0.2 here, and then here we have 0.2. Okay, so since we have this signal stretching between 4.4 divisions, the total voltage will be 0.44 volt or 440 millivolt. You multiply with the volts per division. Now the peak voltage is half of the peak to peak voltage, and RMS voltage is Vm by root 2, which also can be obtained. Now I am setting the time per division to 1 millisecond. Total divisions are 1, 2, 3, 4. So we have 8 divisions from 0 to t. So 8 divisions into 1 millisecond gives 8 milliseconds as a time period, and the frequency is the inverse of time period. So this is the original figure of an actual time per division knob of the CRO. The phase difference also can be measured. The total provided your comparing signals has to be same frequency. Now here we have two signals being compared, and we can see that the signal is the difference between the signal is 2 time division. So this stretches to 8 divisions totally. So that 8 divisions will be equal to 360 degree. So your 2 divisions will be 90 degree. So your phase difference will be 90 degree, which can be easily identified from the CRO. Now instead of applying sawtooth waveform to the horizontal plates, you are also given the provision of applying another waveform, sine wave, which can be fed externally to the horizontal plate. So in such a case, you will be keeping your mode in XY mode of the CRO, and you will be applying signals to both channels 1 and 2, that is both horizontal as well as vertical plates. You will be applying the voltage, and some figures will be obtained on the CRO screen. Such figures are known as Lissajous figures, and the shape and the pattern of the figure will be depending on the frequency, amplitude, as well as the phase difference between the waveforms or the signals that are applied to the horizontal as well as the vertical plates. So this is one of the example of a pattern that is obtained on the CRO screen. Now if you apply only a vertical signal, you will get a vertical line, and if you apply only a horizontal signal, you will get a horizontal straight line. If you apply sine wave to both vertical as well as horizontal plates, what happens? You will get a straight line which is at an angle of 45 degrees. Because you will have both the signals progressing, both are increasing, so you will have linearly your voltage waveform also will be increasing and reaches the maximum value, and then again it reduces to 0, again it reaches the it increases to maximum value in the other direction, and so it starts from here. Initially it is at A, it is a point, starting point, so it increases, reach the maximum value, and again come back to 0, it reduces, reach the maximum value, again come back to 0. Okay, so that's how you get a straight line, which is at an angle of 45 degree with respect to the horizontal angle. Now if you are applying two signals, that is if you apply a sine wave to the horizontal plate and you apply a cos signal to the vertical plates, you have a phase difference of 90 degree. So once you have a phase difference of 90 degree, you will have a circle being created on this CRO screen. Okay, so if you have no phase difference, you will have a straight line, and if you have a phase difference of 90 degree, you will get a circle. So this we have already explained. So here we have voltage, here we have to the vertical plates we are applying double frequency when compared to the horizontal plates. So when you start from 0, you reach the point 12, your horizontal plate has reached this value 12 only, and your signal has reached this point. Again the signal will move through the points and reach 24. Here it will reach 24 here, and here it will reach 24. So you will have such a pattern being formed on the CRT screen when you have multiple frequencies. So instead of a single ellipse or a single circle, here we have multiple signals, multiple loops. So if you have a phase difference between the signals, you will have an ellipse formed. Here we have a phase difference which is between 0 and 90 degree, so you will have a ellipse formed in this axis, in this direction, and when the phase difference is equal to 90 degree, you will have a circle. And these are the different patterns that you can think of, which can be seen on the screen with changes in magnitude, frequency, as well as the phase. Now frequency can be measured with the help of this Lissajous pattern. So once you obtain the Lissajous pattern, you draw two tangents, horizontal tangent and the vertical tangent, and you see the points at which the horizontal tangents are meeting the signal. So here you have 1, 2, 3. So this is 3 tangents are in the horizontal direction. You have 1 tangent in the vertical direction. Now the frequency of vertical signal divided by frequency of the horizontal signal is given by number of horizontal tangents by number of vertical tangents. So this is 3:1. So here you have 2 horizontal tangents and 1 vertical tangent. So this is 2:1. Here you have a single horizontal tangent and you have 3 vertical tangents. So this is 1:3. Here also you can see that here you have double the frequency. So here we get 2 horizontal tangents and 1 vertical tangent. So here Fy by Fx is equal to 2:1. The vertical frequency is double the horizontal frequency. So that relationship can be obtained. And if you know any one of the frequencies, we can calculate the other one. So here the phase angle also can be computed using the this particular Lissajous pattern in XY mode. So phase angle is given by sin theta is equal to y1 by y2. Phase angle is the phase difference between the two signals which is applied. So y1 is this measurement that you take, and where your ellipse is crossing the axis, and y2 is the maximum value of the signal corresponding to this axis. Okay, and sin theta is given by y1 by y2. And if you are having a circle, your y1 will be equal to y2. So in such a case, sin theta will be equal to 1, or theta will be equal to 90 degree. The phase difference between the two signals will be equal to 90 degree. So we have already seen that if your phase difference is 90 degree, you will get a circle. And from 0 to 90 degree and from 270 to 360 degree, that is in quadrant 1 and 4, you will be using the equation sin inverse y1 by y2. Theta is equal to sin inverse y1 by y2. And from in quadrant 2 as well as 3, you will be using theta equal to 190 minus sin inverse y1 by y2. Okay, because your ellipse, the direction is changing, you will be getting this angle. So in order to find out the actual phase difference, you have to use this particular equation. Now as the phase difference is increasing from 0 to 360 degree, from 0 up to 360 degrees, you will have these patterns being formed. From 0 to 90 degree, you will have an ellipse. At 90 degree, you will have the phase difference. At 90 degree, you will have a circle. Then again, at a phase difference of 190 degree, you will have a straight line, but in the opposite angle. Here also you have an ellipse. Again, you will have a circle at 270 degree, and finally a straight line at 360 degree. So this is how you obtain different patterns on the screen with same frequency but different with different phases. Thank you so much.